Hey, well, welcome everyone to this. Thanks for your time. We're quite excited about what we have just released this week. It's a significant upgrade to our existing EXata product, and I'd like to take you through what's new and what it can mean to you, and show you a couple of demos at the same time. So I hope you will find this worthwhile. I know we do have some existing customers on the line. I know there are a couple of people who may be new to Scalable and not completely familiar with what we do. So just before I get into the details, I'd just like to take one moment to give a little bit of background about the company. So you can see along the top line of this cover slide, we do a lot of work in many different critical areas for government, for industry, for the military, for education. A lot of emphasis on protecting networks, on modeling and simulating how communication networks actually will perform in the field, protecting critical infrastructure, developing new battlefield communications. And it all goes back about 20 years ago, when our founder, Rajiv Bagrodia, developed a technology to run network modeling in parallel so that you could build large communication networks without sacrificing accuracy and run these very large scenarios. And since then, we've been extending this basic product tremendously. And so the use cases for our tools range from development to analysis of alternatives, future technologies, cyber assessment, which is becoming more and more important. And it all boils down to two core technologies: the network simulation. So this is our core competence, being able to simulate networks in real time or faster with high fidelity libraries of protocol models which run on them. The ability to connect out to other devices, whether it's live networks, whether it's humans in the loop, whether it's constructive simulations, and also simulate attacks and vulnerabilities in this network so that you can assess how they would respond to real cyber attacks and develop defenses in advance of them and train operators in how to protect networks. Our customers range through all of the services, military organizations around the world, all of the defense contractors, as well as Fortune 500 companies looking at future communication technologies. And what sets us apart from anyone else really is the accuracy of our network emulation, the ability to scale to very large scenarios, and all of these models that we have been developing and improving over the past 2 decades. So we call our technology a network digital twin. So let me explain for a moment what that is. It's a software representation of the actual communication network, whether it's a wired enterprise network, whether it's a tactical network, whether it's undersea. And this digital twin behaves exactly like the real physical twin. And the key to it is that you can keep it updated in line with how the real network evolves and do all sorts of what-if analysis. So we can run our models in real time to connect live equipment. We can run them faster than real time to do all sorts of analysis quickly. And we can predict how these networks will perform under all sorts of conditions which might perturb them. We've got multi-domain waveforms, so we can go from the seafloor out to space and everything in between and model these comms accurately. Because we can run in real time without sacrificing the accuracy, we can connect to live devices like live battlefield radios, real applications for command and control. Even training simulators can be hooked up. And we can scale to very large tactical and enterprise networks without sacrificing the fidelity. And that is important because if you're doing analysis on just a small part of a network, it doesn't necessarily retain validity when you get into large numbers of nodes. Importantly, we can simulate electronic warfare and other cyber attacks so that you can assess how the network will perform under these conditions and train people to recognize attacks and defend against them. We can do spectrum analysis so you can look at the RF environment and how it is impacted by interference and terrain and adjacent frequencies, and configure your electromagnetic environment in the most optimal way. And also, very importantly, we can integrate cyber with kinetic domains. So it's a little bit different than protecting a corporate network where you're mainly concerned with data exfiltration. In a kinetic domain, you're concerned with perhaps weapon systems and sensors and how the cyber attacks are going to affect them and how that is ultimately going to play out in the context of a mission, which is a very different problem from typical cyber protection. And finally, our tools can be used in advance of deployment of new technologies or even installations to help optimize the deployment. So if you're putting in new 5G network, you can look at the urban terrain and the complete exact building structure and plan where you're going to put in your G-Node Bs to help optimize the coverage and the performance. So we've got real-time interfaces. And just a question, can you see the top line of my slides? Because it's sort of obscured on my screen because of the Zoom control.
Looks good.
Yeah, I can see the title. Yeah.
Perfect, thank you. So I just have to remember what the title is. So it's Network Digital Twin Real-Time Interfaces. At the heart of all of this is our EXata engine, which implements the Network Digital Twin and can communicate in real time with a huge variety of outside systems. So in the top left, Constructive Simulations, these tools which model the battlefield, we've integrated with everything shown here on this slide in real time, providing the comms simulations for them. Humans in the loop, you could have red versus blue teams putting in cyber attacks and defenses to the modeled network in EXata and using this as a cyber range or training platform. We can hook up live networks and live equipment like computers or tactical radios or smartphones. We can interface with physical system simulations. So if you're looking at a control system or a SCADA system, we can provide the communications for that and the cyber attacks and see the way these attacks can play out and how they would affect the dynamics of the connected physical system. Very important for power grids and general critical infrastructure. You can use real tools like Wireshark on this, like you would on a real network. You can hook up to the internet for connectivity. We've got an interface to our partner company, AGI, and their STK for satellite communications. We can hook up and connect with traditional cyber ranges and also run live applications like battlefield applications unmodified across our network digital twin. Now, to create a network digital twin, in the past, we were limited to building it from scratch using our scalable GUI. That option is still available, but we've done a lot of work recently to improve the user experience in the context of a digital twin, which can automatically be kept up to date with the live system or network. And so we've created a couple of tools that fit into this as well. So Scenario Importer can take in various external sources and automatically build a model of the twin. So you can connect to a live network, for example, and scan it with any number of tools, Nmap, SolarWinds, and so forth, and get that information about the live network, convert its topology, and build a digital twin ready to go from that in a few seconds. Same thing with a Visio diagram. Same thing with other network simulators. And if you're running constructive simulations, we can connect and hook up and get information about PDUs, about entities and their radio equipment, and again, build the equivalent network. And we've recently added additional capability. We can pull in live network traffic using NetFlow or PCAP files. We can bring in some device configurations. We can bring in live firewall rules to configure firewalls in the model. And we're expanding this in the future. The things marked in gray are not there yet, but they will be there soon. Mbse Tools, so you can create a model of a network or a system, bring in the sysml, convert it, and get the network digital twin. And we plan to do the same thing for actual vulnerabilities off a live network scanned with tools such as Nessus. So our roadmap is the following. We have two primary initiatives. EXata has typically been sort of a single desktop application in the past, and we're splitting that up. There's more and more cloud computing. There are people who don't want to install software locally. People want to do web access through a browser to get answers. So we've taken all of this into account in our latest product. And so we've split up the functionality, which I'll explain in a moment, to make it easy to create these models, analyze them, get results, optimize the results. And it also allows us to split up the product for specific user classes with different expertise. There might be a network engineer who needs all of the detail and is building their own models. You might have somebody looking at wargaming. There might be somebody looking at network planning. So you can have people with different expertise using different components of the system. You can also have different combinations of tools and models for different verticals. So somebody planning a 5G deployment can have a very specific tool for doing that. And of course, there's the very important cyber assessment. So we can build cyber ranges for tactical networks and weapon systems, and also for enterprises and SCADA systems. So what does this ecosystem look like? So originally we had our Scalable GUI and our EXata engine, and look how it's grown since then. We've split this up based on expertise. So you might have on the left side the most sophisticated types of users. So they'll use a tool for designing scenarios. And as I mentioned, they can bring it in from all sorts of different sources. They can modify it using our GUI to do all sorts of what-if analysis. And we've split up our previous all-encompassing configuration into different parts to make it easy to put them into libraries. So you can have network topology, which is different from the traffic on it, which is different from device characteristics, which is different from the environment that it will execute in. So the scenario designer will save all of these as libraries. And then the experiment designer, who might not have quite the same expertise, can pull up these pre-created objects from the library and put them together to create an experiment. So as an example, I might have a network defined with tactical radios, and maybe I'm running it in a desert, and then maybe I want to move it to an Arctic environment or a mountainous environment. I can keep the network topology, I can keep the mobility and just move to a different area of the Earth and bring in all of the terrain, and I can do an experiment there and I can compare the results, or I can change characteristics of the equipment and see the difference. So the experiment designer will build these experiments, put them into a library of experiments, and then you could have even a less sophisticated user who's actually running the experiments and doing the analysis. So our EXata engine pulls the information from the experiment configurations, runs, and you can interact with a couple of new tools. There's Inspector, where you can query to find out routing tables and so forth. You can visualize and get an operational view of the network in the context of the mission with platform movement and terrain. We can connect to other simulations and other devices with humans in the loop. And the end result of all of this is a very detailed statistics database as to the performance of networks and devices at every moment in time in as much detail as you want. So then you can analyze that, and we've got tools to help you analyze that, to automatically generate heat maps and so forth, and help you to go back and make changes to get the sort of results that you're looking for. And this also has a report generator so that you can export information from this into reports to superiors in different formats. And we're moving towards a web-based interface. Just about everything that I described on the previous slide is now web-based. So you can just open up a browser and you can have different tools available, which you can go through in sequence. Or if you're, say, a less sophisticated user, you can start halfway down and go through it. And you can view what's going on. And the way it works is there's a web front end, there's the back end, and this talks to the simulation engine to run the experiment and sends the user back the visualization, the analysis, and so forth. Okay, so now let's get into the details of what's new in our latest release. We've put in a number of enhancements in various areas, particularly in 5G. We've had a lot of interest in the 5G model, which was introduced in our last release 7.2. And so we've enhanced that, and I'll get into the details in a moment. We've done a lot of work in cyber resilience because there's a lot of interest in this right now. So we've made some significant advances in our cyber modeling. There's the web-based experiment design. There's a way to automatically replicate designs. So you can bring in from sources and you can export as well. And we've upgraded the RF modeling. So a little bit more detail on these. In the 5G modeling, we've now implemented beamforming. We used to have an abstract model for that. Now it's no longer abstract, it's physics-based. And so we can create the beams with their characteristics, the spread of the beam and so forth. And this is very important in tactical networks because you don't want an abstract model which is going to tell you, yes, you're getting a good signal. You want to know whether the opposing force can pick up that signal. So you need the directionality of it and its intensity and so on. You need to know whether jamming is going to work against it. So having this higher fidelity beamforming allows you to do that kind of analysis now. We've also implemented network slicing because that will be implemented on real 5G networks, and you can take the same physical infrastructure and support various applications which have very different quality of service requirements on the same physical hardware. For the cyber resilience, we've got a brand new graphical attack editor, which allows you to create attacks with the logic, with a sort of flowchart view, and I'll show you a demonstration of this. And it allows you to replicate real-world attacks without doing any coding at all, just graphically putting the steps together. And of course, doing experimental attacks, things which may not have happened in the real world yet, but which you want to anticipate. We've created a new attack, phishing. This is important because the way malware gets into systems is almost always through phishing, where you've got malicious emails. People don't recognize that they're malicious. They click on a link or download some software. We've got models and we can actually bring up emails now on live workstations connected, and these can be malicious, and if people click on them, we will model the malware, and I'll show that to you in the demonstration. For scalability, we can also do the same thing with simulated humans, so you don't have to have a live person at every single computer. You can have simulated ones with simulated behavior, a probability of falling for these malicious emails, and so forth. We've also got a couple of new attacks. We've got ransomware. So upon successful attack, it'll start locking up the hard drive and encrypting files, and you can actually see that happen. And we can model backups or second generation backups to help protect against that. We've also got models for data exfiltration. So this can help train for or identify advanced persistent threats where they are slowly extracting information from your confidential network. And also, we've developed a new seamless interface with two tools, Viral and GNS3. And these are tools which provide emulations of routers and switches, and they have the virtualized iOS models running on them. And this gives us a very big advantage because we can now bring these into the EXata scenarios, and you can exploit vulnerabilities in the native iOS that would be running on the router. So you can use real tools to exploit these, and this all works perfectly with EXata, and I'll give you a demo of that as well. For the web-based experiment design, we've really looked to simplify the analyst's job and make it really easy to create and run experiments and analyze the results. We've incorporated VM management. So just like I mentioned with the iOS, you can incorporate VMs with traditional operating systems and make these part of your exercise, and again, be able to use vulnerabilities in those images and exploit them as part of the cyber analysis. And we've also made it easy in line with our roadmap to be able to move seamlessly from one execution environment to another. So from your desktop to a server to the cloud, setting up resources, setting up hardware in the loop, and so forth. For the automated design replication, we've had for a while the ability to bring in Visio files and automatically create EXata models from them. Now we've done the opposite, where you can take EXata models or modified models and export them back out to Visio. And I'll show that to you as well. And the advantage is if you're doing planning for an upgrade to your network, adding devices, reconfiguring things, you can do it all in EXata, press a button, and it generates a new diagram back in Visio for your documentation or approval. In terms of upgrading the RF modeling, we've got a new model for rotating antennas, which is important if you're operating in an environment which also has radar, because there is interference between radar and comms, and this will accurately model it and actually help develop some mitigation strategies like cognitive use of the spectrum. We've also got Cdb Terrain now, which is a standard which is used in a lot of military simulations. And it also makes use of open flight databases, which are used in a large number of simulations. And this enables us to bring in these existing databases, which have already been created for other uses. And these are geospecific, so you can get them for specific cities, for example, and do your path loss modeling with both the natural and the urban terrain, both of which are contained within Cdb. We've upgraded our analyzer to be able to visualize not just the RF heat maps, but also the interference among nodes, because that is important for planning purposes as well. We've added some additional capabilities to our scenario player. An important one is that we can show the message completion rates dynamically as you're running the scenario. We used to just show the data rates, which didn't tell you as much. Now you can see at a glance if there are portions of the network or times when you're running into problems. And also, we've updated our SIGINT model, signals intelligence. So instead of just giving you a report in the output window of EXata, it will also store the results in the StatsDB, so you can get all the detailed results for analysis. Okay, so that's the overview. Let me get into some more details and some demos. So first of all, what we did in 5G. So there's beamforming. In the tactical battlefield, very important because you have these beams illustrated here, which gives you a lower probability of detection, more resistance to jamming. It's also important in the commercial world. Beamforming is important in V2X, where you're trying to communicate with moving vehicles, so these dynamically follow them. We've implemented the ability to customize these beam patterns, and of course they work with our path loss models and the interference, and importantly, malicious nodes which are trying to disrupt or learn information from the communications. In terms of network slicing, this is an important capability because you can have contrasting applications sharing a 5G network. So by modeling this now, you can research how the performance is going to get affected before you deploy the infrastructure and see how the simultaneous competing applications will behave. So we ran an experiment, for example, where on the same infrastructure, we ran an EMBB case simultaneously with a URLLC case. And because of the network slicing, we were able to achieve the demanded latency of less than 1 millisecond for the URLLC. And of course, if you change priorities and so on, this changes a little bit, and then you don't necessarily meet the specs. So we can analyze situations like this. So let me move into the first demo quickly. Beamforming. So here's a scenario where we've got a 5G network. It's got the core, it's got the RAN modeled here, and we've got this new parameter here, enable beamforming using a directional antenna. So we've set this to yes over here, and then you can give it the specific antenna pattern that you have defined. And it'll use this as it forms the beams to the various UE equipment. So if we if we run the scenario, over here on the upper right is the core, the lower left is the RAN part, the Gnode B is in the center. You can see there are applications running to UE1 and 4. Let me just pause this for a second to finish explaining. So if we look at the geometry of this, the Gnode B is in the center of a number of UEs. 2 of them are receiving data. 1 of them is towards the north, 1 is towards the northeast. So the beamforming is going to point towards these. And we've inserted 2 SIGINT receivers, 1 more or less in line with UE4 and 1 on the opposite side of the Gnode B. So because of the beamforming, SIGINT 1, because of its location, will likely be able to pick up the transmissions to UE4, not necessarily to UE1. SIGINT 2 should not be able to pick up very much in this scenario. So if we look at the statistics, or not the statistics, if we look at the SIGINT results of this after running the experiment. So we have time-stamped data. So we've got, at the same time stamp, we've got the 2 nodes, 13, which was the one up here, 16, which was the one down here. 13 reports a signal of -73 dBm. So it picked up some information over here. SIGINT 2 reported much less, -106 dBm. And this confirms that our directional antenna and the beamforming is actually working. So this sort of scenario could be used in a tactical environment with opposing forces to understand better what they could pick up or disrupt. So that's the first demo. I'll just continue. Cyber enhancements. So we've got a new adaptive attack flowchart editor, which I'll show you. We've got the new phishing email attack. So we've got simulated human responses, which allows you to scale up these target networks and analyze them for cybersecurity. We've got propagation. So if somebody actually clicks on a phishing email, it can propagate through their network and infect other or send messages to other users as well, where they could click. We've got the ransomware attack. We've got this new operational host service, which allows EXata to interact better with live humans. So we've got this communication interface. We've created an email service, so we can send realistically looking emails to the humans, and we can capture what their actions are and use these to affect the way the attack propagates. We've also got this automation for VM management, which we implemented using Vagrant. So that enables you to bring in VMs with specific OS vulnerabilities. We've got the seamless interface with Viral, which I'll again show you. We've got the data stealing application. So this is a screenshot of what the attack editor looks like. So you can create these trees over here with different outcomes connected to different actions following that. And these can become as complex as you want. You can create loops and so on. You can put in delays, so you can actually have cyber attacks which are very stealthy, where the results are not relatable to a particular action. And you can use these to recreate, and I'll show you an example in just a few seconds. This is what I'm going to show you. It's a representation of an attack which happened in the Ukraine a few years ago, where Russian hackers were able to get into their control system for the electrical power grid and actually shut down parts of it at various substations. And the way this attack worked is, as usual, they sent emails to the corporate network, which looked valid, and some users clicked on these. That installed malware, Black Energy 3, which then enumerated the corporate network, infected various hosts, set up backdoors, grabbed credentials, and from there was able to get through the internal firewall to the SCADA network, where another backdoor was created, and they were able to take control over the human-machine interface and take control of it and shut down breakers and relays and actually shut down power over here. They also did simultaneously a denial of service on the telephone system to keep the operators more in the dark about what the actual extent of it was, because customers could not call in. So we've actually modeled this. Let me show that to you. So here's that network modeled in EXata. Now we've got a new capability, which is from the Tools pull-down menu. And this enables you to create these adaptive attacks. So it's down here. And you launch that, and it opens up a GUI where you can create these. This is one which was created before, but I'll show you the steps to create one from scratch. You can have any number of these in the same scenario. You just click on this plus to create a new one. And that will give you a red square, which is the root, really. And then you can build on that and have certain triggers. You can click on this, and there's a pull-down menu of templates available. So we can choose different attacks. In this case, we're going to steal user credentials, which was the first step in the attack. And then you've got what to do if there's a success or a failure on this particular exploit. And here I'm doing one with NetScan, where it's got a third option. As it starts scanning the network and you get a response to a ping and you've got an IP address that replies, you can take different actions. So it's just a pull-down menu, easy to use. Here we have IP scan. So if there is a response, you can create a new attack block. You can customize it. So here the attack type, the source node, you can select from any of the ones in the scenario, configure it for IP addresses and so on. So here is the way you can create a new attack box. It creates a new box over here where you can give it a delay. You can clean up the appearance of this if you like. And again, you can do a pull down and create specific attacks with specific outcomes and the way this feeds in. So you can progress like this. I'll just show a couple of more things, putting in a couple of more boxes. And you can connect the outcome of one to the input of another, and you can create all sorts of loops and logic over here and really create a state machine for how this cyber attack will progress. And here's how you create a phishing email. This is a new type of attack under the social engineering umbrella. We've got two in there right now, hacking, where you can infect a web server, so that if somebody goes to that IP address, they will receive the malware. You can also do a phishing email attack, and you can compose it here. You can select the victims for it. You can set this propagate to victim side to be yes, where the email will propagate from one user to another in their address book and move through the network to open up other ways of getting the malware in. So you can configure on the EXata side the user profile. We've added some additional capabilities into there, like susceptibility to these attacks. So here's an external machine which gets mapped to a node in EXata using the connection manager. Connection manager gives you a list of all of the nodes on the EXata side. So you can become one of them just by clicking on one of them and saying set default. And up in the upper right, we've got this new capability where on the user's machine, we've set up an inbox. So as soon as they become a user, this inbox starts populating with emails coming into them. So you can see some of them showing up over here. And you can see the traffic moving in EXata. And so the user now can launch the attack script, which they created, which was this one, the node shutdown. And it gives us a status. So it has launched these emails over here with the intention of stealing root credentials. So you can see the victims it's been sent to. If we go back, the email inbox has populated with additional emails. This is the malicious one. Somebody clicks on it. It looks like a real email. And there's the capability to download the attachment. So if somebody actually clicks on this link to download the attachment, we'll see what happens on the EXata side. That is going to signal our script. And now you can see there's a lot more attacks propagating through the network. The different addresses which have had successful attacks against them. We can see if they're unsuccessful ones, why it did not happen. And you can see the way the attack is progressing with all of the steps that we have programmed in without doing any coding. So here in the EXata GUI behind that, you can see what happened. The attack has actually progressed, and it has had the intended shutdown of the nodes on the SCADA side. Another thing we've done, which is also related to cyber, is this seamless integration with Viral. So Viral enables you to have a virtualization of a Cisco device. We can do the same thing with GNS3. And it becomes fully integrated into an EXata scenario through hardware in the loop, such that we can exchange routing tables with it. We can send traffic through it. And we can also, because it's running the actual iOS, we don't have an abstract representation of it. So we can use real attacks against it in the safe EXata environment and see how that can affect the entire network. So this is a way of increasing the fidelity of cyber analysis and training. And I'll show you a demo of that as well. So here's, oops, let me just back up for a second to explain. Here's an EXata scenario where we've got the Cisco router mapped to real hardware. We've got the rest of this modeled in EXata. And if we go over to the Viral GUI, we've got the router configured over here in the middle, and we've configured two interfaces on it, which have been defined over here. And these two interfaces are mapped to the two links in the EXata scenario, which are shown as connections from the EXata mapped node. These are the things that you need to accept, these three items, in order for this to work with EXata. So I'm just highlighting that over here. And now we can start up this virtualization over here in Viral, and it'll start running. We can open a command window and see the messages coming from it. So that'll show up in a moment. So just as if it were a real router and we've connected, you can get this information, and we'll see how this reacts as connected with EXata. So over here, we can start the EXata scenario running. And now it has picked up the 4 additional routers, which it's connected to. It's identified them over here in the screen. And traffic is moving through. Both live traffic and simulated traffic is being routed through this virtualized router over here. We can get further information from it just to show that everything is being exchanged as if the whole system together were live. So we can look at the OSPF database over here. Confirm, we can look at the link states over here for the different connections. And we can see the state is full for these 4 adjacent routers. And we can show the actual routes over here for the different subnets. And we can also go back to the EXata side and use our recent tool, the EXata shell, to gather information as well from here, from this console. So this is the EXata shell. We can do the show routes, and they're picked up from here. We're exchanging everything using OSPF version 2 with the virtualized router. And we can do some pings. So we can ping node 14 from 19. And we'll start that off. And as it's executing the ping, you'll see the blue arrows showing the actual traffic. Here we're getting the response times from it. And it's moving the pings and then the responses back. And then I'll just advance a little bit to save time here. And we can do the same thing from the Viral side. We can ping from here, and essentially the Viral router works seamlessly with the information in the EXata scenario and the EXata routers. Okay, so that brings me to the web-based experiment designer. So again, I've got a demonstration for that. So what we've done is we've gathered functionality into two basic areas. There's library management, or the scenario design, where you put together these objects in the library. So we've got network configurations, which are the topology and the virtual devices, the model devices. So you can bring these in if you've created them elsewhere, say using the classical GUI or importing them from various sources. They become available in the library to be used for experiments. So here we're just choosing a file, giving it a name over here and saving it. And so this becomes one of the network configurations available. For the devices, these are the live devices. They can be physical or virtual. And again, you can give them names, document them, give them an IP address. So there might be a set of equipment in your lab that you may connect on occasion to EXata. So you just define them once over here. You can give them an image. You've got cyber attack templates, which you can define and populate over here. So we've got this new capability to create them from templates or from scratch. Host profiles, so you can define vulnerabilities and services. User profiles, so these are the simulated users with their behavior in email exchanges and browsing websites. You've got terrain, so you can define different coordinate corners for your scenarios and import the terrain for them and save these as different terrain profiles. And the same with traffic profiles. So you could have live traffic profiles that you've imported. In this case, we're importing a PCAP file, which can then be used on the simulated network, or you can scale it up or down. So having done that, you move to experiment design. And this is where you build an experiment from things which are in the library. So there's these tabs across the initial setup. So you just give it a name. You give it an execution environment, if you like. So we'll select the cyber network configuration for it. We can run in simulation or emulation mode, select it over here. We can bring in the live devices for hardware in the loop. So you just choose one of the pre-configured devices over here, and you just map it to one of the nodes in your network configuration. And you can define key performance parameters. So you might be interested in some particular statistics for your kind of analysis. And you can select these to operate at the system level or at a particular node. And you've got a pull down list so you can select whatever you would like to analyze. And you can have any number of these available for your analysis. So having done that, you can move over to experiment control. So here you can load up an experiment for running. So we've got this one ready for execution. It's the cyber. We just click on run experiment, and this will start initializing it and doing error checking on it. And then it'll show under the ongoing experiments. We can start it up over here, and we can view details about it. So we can see there's a check. We had some hardware in the loop, so it tells us the device was successfully mapped. It checked the network, so it can communicate with it. So you can make sure before you start that everything is working properly on your network. And then you can see the simulation log. You can monitor what's going on if you choose, or you can just wait for the execution to finish and then move into the analysis after that. So here it's finished. And what we'll do is, at this point, we'll go over to the analysis and look at some graphs. So we've got this experiment cyber, which just ran, a previous experiment DTAD, which had run before. We can compare these. So we just click on analyze, and it's already picked up the KPPs that we had defined. So we can compare the two different experiments using the same KPP, and we can see how this evolved over time. We can look at a single experiment at a time if we like, just by unclicking one of these. And we can look at other KPPs as well in the analysis. So combine all sorts of graphs here. And last thing I didn't mention at the bottom was the VM management. I don't have time to show that today, but that enables you to create VMs, set them up, and use them as hardware in the loop. Okay. Visio. So we've had the capability to import Visio for a while. Now we can export Visio. So you can make your changes, you can add devices in EXata, run your analysis, say, okay, this is the kind of network that I want, and then you can export it to Visio. And you can send this around your organization for approval or comment, and people can view this without needing additional EXata licenses. And so I'll just show that to you. So here's a configuration done in EXata with a number of different kinds of devices, wired and wireless. We've got this pull down export to Visio. So you can just give it a name here, save it wherever you want. And we'll use a file for any association of imagery that we want to use. It took just a couple of seconds. We can open this up in Visio, and that's what it looks like. So we use some of the Visio icons for this, but if we compare it with the EXata scenario, it is exactly the same topology. It's the same relative positions on the canvas, same node names, same connections. So you can move back and forth between Visio and EXata freely. The second option is similar, except you can tick use icons from the configuration file. So if you've created some specific devices in EXata, which are not found in Visio, maybe you're doing a tactical scenario, maybe you've got aircraft and tanks, you can export these to Visio. And here we've used the exact icon representations that we've used in EXata, and they are copied as is over to the Visio diagram. Okay. Okay, so now about our RF modeling. So radar interference on communications is important, particularly in military scenarios, but even in civil scenarios where you've got air traffic control radios, radars on ships and so on. By adding the rotating radars, we can have more realistic battlefield scenarios. You can analyze some of the techniques for sharing spectrum and define or develop or refine technologies for signal sensing, accessing the spectrum dynamically, or developing cognitive communication algorithms. The other thing on this slide is the Cdb Terrain, which is the standard terrain. It includes imagery, altimetry, material information, features, lights, 3D models. So these are the kinds of things which are used in it, shape files, open flight models, and so on. This enables you to use these geospecific databases for 5G planning or for wargaming scenarios. And we've got heat maps with interference, which I'll show you. And we've got this dynamic message completion rate. So I'll show you the last couple of demos now. So the rotating antenna, you can see that as it rotates, the power from the radar is going to be hitting different communication assets, whether they're transmitters or receivers, and it's going to affect the interference, but it's periodic. And so some of these nodes could communicate effectively while they're not under the radar beam. So by modeling this rotation as well as the movement of the entities, we can have realistic scenarios to analyze this interference. The next thing I'll show you is the Cdb Terrain. So I'll do that live. So this is a new feature. So here I've imported geospecific terrain. Let me just go to a 3D view, which I can't see because of this 3D view. So here we've got the natural terrain as well as the urban terrain coming from the CDB. So you can see you can have complex urban representations, all sorts of objects over here. And these are pre-existing databases, which you can just import with one click into EXata. And all of these, the natural terrain and the urban terrain, will affect the RF propagation signals as the nodes move around in this terrain. The other thing I'd like to show you is the interference. So this is our scenario analyzer tool, which takes the output, the StatsDB, from previous runs. So I can go, let me just go large here. I can go, we've got a worldwide database of satellite imagery and terrain. I can take one of the previous databases, and it'll interpret that, and it'll move to that area of the world where the scenario took place. It'll show me all the nodes which are in the scenario, as well as the frequencies which were used. Here I chose 2 close frequencies so that we would have interference. On one of these channels, I have a small number of nodes, 5 of them. On another, I've got all the remainder of the nodes in the scenario over here. So I can select one of the entities. Let's say it's this helicopter, and I can select interference over here, and we'll see what that looks like on this particular terrain. So the helicopter is actually in the center over here at node 5, and it's just reading in all of the data right now. There's extensive data in the database, and it's going to render the interference in just a moment. So you can see as I zoom in, close to the helicopter, we don't have to worry about interference. Our signal is strong enough that it'll overpower the weak signals from these other transmitters. As we get farther away, the interference becomes more important, where you can see these red and orange and yellow areas around the other sources of RF energy, which would affect our ability to clearly communicate with the receiver in those areas. And this can be shown in 3D over the actual terrain. So it gives you a good representation of how you can expect the communications to happen. And of course, you can do this different altitudes and slices and at different times in the scenario. And I think the final thing I wanted to show you is this message completion rate. So we've updated scenario players so you can have different traffic flows of different types shown in different colors for clarity. And you'll notice if you look carefully, and I'll zoom in just a moment, besides just the bits per second that we normally show, we're now showing an MCR, message completion rate. So this is changing dynamically, and it gives you a good indication. Over here, the network is working well. Over here, not so well. So you can see over time at a glance where you're running into problems. So that's really what I wanted to cover. There was a lot of material there and I had only 1 hour, so I went rather quickly. But I'd like to thank you all for your interest and your patience with this. And we can open it up to questions.
Thanks, Lloyd. I'll just take a few questions. For those of you that don't have my email